Okay, so for this particular chapter from the book and everything, it's not going to be so bad. This does heavily overlap with anatomy, so hopefully some of this feels at least somewhat familiar. But let's go ahead and get into the central nervous system. So for this video, we're just going to kind of remind ourselves, just introduce ourselves back to the central nervous system. And throughout the rest of these videos for this week, we're going to talk about the regions of the brain, the cranial nerves, different things that contribute to protecting the central nervous system, as well as get into cerebrospinal fluid, different cavities, some development, and whatnot, so that we can just get more familiar with the central nervous system, kind of remind yourself of a lot of parts. So for this video, we're going to focus on just, again, reminding ourselves. So let's get into the central nervous system. Remember, there's only two parts to this, the brain and the spinal cord. Everything else is going to be peripheral. And so the central nervous system is really just going to be involved with receiving information about the world around us, what we're sensing, what we're experiencing, and then integrating that together from multiple senses, kind of building a picture, building the big picture, and then making a decision on what to do in response to those sensory information that's coming in. So really the main thing we see is the interneuron. The interneuron is the one that is doing that processing. Remember the type of neurons. We had sensory, interneurons, and motor neurons. The peripheral nervous system we'll get into a little bit later. That's a different week. But that's where we get into the nerves themselves, ganglia, receptors, all that kind of stuff. So let's kind of just remind ourselves of the different parts. So there's some main components. There's a cerebrum, also called the telencephalon. I'm just going to call it the cerebrum. This is the big part of the brain. This is what you're thinking when you think brain. All those wrinkled parts, what I like to call the thinky bits, is going to be the cerebrum. And if we go further in towards the middle, we get to the diencephalon, where we have the thalamus, the hypothalamus, and the epithalamus. We also find the pituitary gland kind of hanging off of that. We then have the cerebellum, which is going to be this piece we see just kind of posterior and inferior to the cerebrum. And then the brainstem, which is more kind of central and then leading down towards the spinal cord, right? This is going to be that continuing piece from the brain to the spinal cord that has three main parts: the medulla oblongata, the pons, and the midbrain. And again, we'll go through all of these, kind of talk about what they do and whatnot again. We also have 12 pairs of cranial nerves, most of which are part of the peripheral. The only two, so the olfactory nerve and the optic nerve, those two are technically central nervous system, but the other 10 are going to be considered peripheral, right? So this is going to be that connection. That's why we call them nerves, right? Because they are peripheral. If it was part of the central nervous system, they would be called tracts instead. We will spend some time talking about these, so I'm not going to go into this, but you should know them, right? You had to know them in anatomy. I'm going to have you continue to know them now, right? Know their number, know their name, know if they are sensory, if they are motor, or both. Some of them are both, or what we can call mixed. And then, what do they do, right? What do they help control? We also have protective components. So if you really think about it, the central nervous system, it's so vital. It does all these really important things for us. It really commands and controls the rest of the body. So it makes sense that we would really want to protect the central nervous system. And so we have lots of different things that can help with that. We have the cranial and vertebral bones, so bony tissue, just hard against like physical damage, right? Something can't just come in and squish in to any of the tissue of the central nervous system. So we have a hard covering. And we can include like skin with that too, right? Because skin's going to be over the top of that bone, providing some protection. We have the blood-brain barrier again, so we have an kind of added effect where rather than just having normal capillaries that go through, we do have cells, remember those neuroglia, that can kind of cover and help provide a little extra protection in terms of what can leak from the capillaries into the central nervous system. We have a more strict, kind of like more strict rules on what can get through with that blood-brain barrier. We have cerebrospinal fluid, which is going to help kind of wash over. We can move nutrients, we can move wastes around to remove them. And it does provide some cushioning, kind of like almost like an airbag-like type protection. And then the meninges, right? These are these three layers. We have the dura mater, the pia mater, and the arachnoid mater. These are, if you're trying to remember the order, I use the acronym PAD, that the meninges pad the brain, right? So dura mater, arachnoid, and pia mater. So going from the very inside out, the meninges pad the brain. We do have the arachnoid space underneath the arachnoid mater, which is where we find a lot of that cerebrospinal fluid. And the meninges kind of, from the brain, they are going to be continuous with the spinal cord. So cerebrospinal fluid can really flow from brain down through the spinal cord area and back up. So let's get into that blood-brain barrier, because this is something I know, at least for me, I haven't really talked about yet, and I didn't talk about in anatomy, but let's go in and talk about it. This is a physical barrier, right? So the capillaries that run through, if you think about everywhere else in the body, right, things can kind of leak out of the capillaries into the interstitial fluid, and we can make all sorts of transfers there. But with the brain, we want stricter rules, right? We don't want just anything to be able to leak out from those capillaries and get in there. We want to be a bit more picky with what can get into direct contact with the central nervous system. So here, right, we see like astrocytes, we see like we're forming tight junctions between the cells. There are some neurons coming into connection with it, but one big thing is we see these astrocytes, one of those neuroglia, that is kind of all together, they're encapsulating that capillary. So that leakiness that we saw in the like rest of the body, it's not as, this is going to be more regulated, right? This is to limit transport of things across, from the bloodstream into the central nervous system. So we have tight junctions between the endothelial cells that make up the capillaries, right? Our basement membrane is more reinforced, and then the astrocytes, right, those neuroglia, they have the end feet that are going to help kind of provide a barrier. And this is going to be a more selective barrier, right, so that harmful substances, pathogens have an even harder time getting through, so that they can't affect the brain. So this also can prevent certain medications from getting into the central nervous system. There's this barrier can be damaged, so things like head injuries or infections like meningitis can cause damage to that, and that can allow things to get into the central nervous system that would normally not, right, and cause even more havoc. But this is something we need to maintain, right, the blood-brain barrier. And cerebrospinal fluid is a liquid, right? This is going to be produced by those ependymal cells. If you remember, we talked about those neuroglia and that we find them lining things like ventricles, and they're the ones producing this fluid, right? This is going to help carry things like oxygen and nutrients and help circulate them around the central nervous system, because we don't have a bunch of blood in there, right? We have cerebrospinal fluid instead. And so how do we move things that are helpful, like oxygen and nutrients and whatnot, and get rid of all the waste like carbon dioxide that we produce? The cerebrospinal fluid. And in fact, as the cerebrospinal fluid cycles through, it will be dumped into the cardiovascular system. It will be dumped into the bloodstream so that those wastes can be removed, right? But again, ependymal cells are the ones that are making this and helping kind of circulate the CSF through, right? So if we take a peek of kind of how it circulates through, so here's where we're being made, right? What we call the choroid plexus in the ventricles. That's where we have ependymal cells kind of going into overdrive with CSF production. All right, and then we see that we flow around, down and around, right? So we flow through the ventricles, we flow through the central canal of the spinal cord, right? We flow through the subarachnoid space, right? So we see we're going down through the spinal cord area, we're going up and around the brain and whatnot after we escape from the ventricles. And then right here, right, we have these venous sinuses, right? And that's where we're going to kind of take this CSF and absorb it into the bloodstream, right? So we're absorbing it in through the arachnoid villi into the venous sinuses so that this blood can be taken, away. We can do things like, return it back to the body so that we can do all the nutrient exchanges that we need to. So how do we see the central nervous system? Because if you think about it, it's the most important organ system we can think of in the body, right? If something goes wrong with it, it can have catastrophic effects. And it also means that it's very sensitive. It's not something we want to necessarily open up. So how do we visualize the central nervous system? So there's a few things we can do. We can use X-ray computed tomography or a CT scan. This is good for soft tissues, so we can see if there's any changes and whatnot. It does use radiation though. Same with the PET scan. If you remember these, all of these actually from the very beginning of the class, the CT scan and the PET scan are both going to use radiation, so it's not something we necessarily are going to use unless we know we need it. The PET scan though, we can use dyes to help kind of label, right, certain pieces. We can kind of find where it goes, and then we kind of create this heat map, right? These are going to be helpful for things like how has blood flow changed in the brain, or how is someone's case of brain cancer going, right? Is it getting worse? Is it getting better? And then MRI. MRI does not use radiation. This uses magnets instead, so there is no risk of, when it comes to developing cancer and whatnot, MRI doesn't carry that risk because there is no radiation. However, because it uses magnets, if someone has metal components, they would not necessarily be able to get this done. But this would create a nice image, right, where we can kind of see, kind of be able to see gray matter, white matter, cerebrospinal fluid, right? We can make distinctions between that. This is also one of the preferred methods of imaging for diagnosing or understanding the progress of someone's MS or multiple sclerosis cases, because we would also be able to see things like lesions that have developed on the brain. Functional magnetic resonance imaging, or an fMRI. So it's similar to an MRI, except this is where we're actually kind of watching it in action. So rather than just take a picture, this is more of if you think of it like a video in a way. So rather than we're taking a snapshot, we're watching how things change over time. So we can see how different neurons are firing in different regions of the brain. We can kind of see basically how blood flow changes, and that kind of tells us which neurons are firing versus others that are maybe not firing as much. We also have the electroencephalogram, or an EEG. This is just measuring the electrical activity. Because remember, we talked about action potential. It all comes down to charge, right? It comes down to electrical activity, and so we can measure that. And so we see we have all these electrodes over the top of this person's head. They, for visual purposes, removed their hair and skin and all that kind of stuff. Obviously, we would not scalp the person. But we have all these electrodes, right, to monitor the electrical activity over all of the cortex, right, over the brain. And so we're looking at, different types of patterns to understand what the brain's doing. So alpha waves, we're active and relaxed, right? Beta, we have visual stimulation, there's mental activity. Theta, we're seeing this during sleep, and then delta also in sleep. So you can kind of see the more you're doing, the more you're thinking, the more you're engaging in mental activity. When we look here, we see that it's whoa, there's more going on, right? All those little peaks and valleys are getting closer together, versus during sleep, right? Dreaming, things like that. It's kind of whoa, just kind of go with the flow. The amplitude might, is still kind of high, maybe not as high. And then we see the wavelengths are longer. You don't need to memorize how that goes though. This is just kind of an informational thing for us to understand, how we can kind of get an idea of how someone's brain is working.